Hi, and welcome to the next lecture unit in the lecture chapter on nonlinear support vector machines, which adds a couple of more details on the Gaussian kernel, which is also called the RBF kernel or radial basis function kernel. So I've already introduced the formula of that kernel before when we discussed the kernel trick. So it looks like this unnormalized part here of the very well-known Gaussian density function that by now I hope you all know very well. It mainly depends on, as a hyperparameter, on this width parameter sigma squared here, which defines the width of this multivariate Gaussian bump function in all canonical directions. We can also write it in this alternative form here, where we are now using the inverse with hyperparameter gamma, and that doesn't change a lot. So obviously gamma is simply 1 divided by 2 sigma squared. And how this works is you compute this squared Euclidean distance here in original input feature space, and then you insert this basically in this univariate Gaussian function here. So this distance here between these 2 points is inserted here. And for that reason, we also call this kernel isotropic, because it only depends on the distance between its 2 arguments. There's also a straightforward extension of the principle where you plug in a positive definite symmetric matrix C in here, so that allows you to kind of control how you scale the width along several customly defined principal axes. So you can basically scale your kernel along any arbitrary axis you want. You probably want to parameterize this here at least a bit through hyperparameters as well, so you can learn the scaling through model selection. You probably don't want to parameterize the complete matrix. That would be very difficult to tune, but at least want to parameterize it somewhat, but I'm not going into this extension here in this lecture unit any further. What I do want to explain is how this guy here works. So the simple basic Gaussian kernel, because that's already difficult enough, and it's the most popular kernel for the support vector machine. And there's a reason behind this, which we'll hopefully discover now here in the following slides. So if we're using such a Gaussian kernel, all RKHS basis functions, which look like this, and which are these bump functions here, are linearly independent. I will not prove this here, so it's doable, but it's not that simple, and for time reasons I will skip that. But this implies that all finite data sets are actually now linearly separable. Does that now mean that we can actually get rid of the soft margin SVM? Because remember, the soft margin SVM we only introduced in order to allow margin violations through the slack variables. If everything is linearly separable, we don't need that anymore, right? That's actually not really true. So the roles of the nonlinear feature map and of the soft margin constraints are actually quite different. So the purpose of the kernel and its associated feature map is to make learning easier by projecting into a higher dimensional, richer, more appropriate feature space to employ our linear learning algorithm there. But even in an infinite dimensional feature space, we probably want to allow for some margin violators, because our data can be noisy, right? So there can be outliers in there. We don't necessarily want to classify everything correctly. If we would use a hard margin SVM and we would enforce this, we'd probably just get a resulting model that overfits our data quite heavily. Okay, what I do want to explain here on this slide is how this RKHS or basis function intuition for the Gaussian kernel really helps us to understand the effect of the RBF kernel, and that the Gaussian SVM actually forms a local model of Gaussian bumps. So what is helpful here is that we remember first how the prediction function for the kernelized SVM is formed. So this is obviously true for all kernelized SVMs, not only for the Gaussian one, but for the Gaussian, this thing here, this has a very specific form, and this is what we now want to visualize. And I want to actually say that this is probably the most important slide here, in at least with reference to the Gaussian kernel, which hopefully really helps you to understand how that thing now works. So what we're now going to do is we're going to visualize this. I've set up a very simple data situation here down below with a couple of green points, which are supposed to be from the negative class, 3 red guys, which are from the positive class. And I now want to visualize how this f function here is step by step added together when we add these components here. So obviously, all of these components consist of such a kxix. So that's the Gaussian bump function, okay? And that's linearly scaled. It's linearly scaled by the alpha I. So that's the Lagrangian multiplier associated with the ith observation, or you could also call this the dual variable. And then there's also this yi here, which is simply the ith label of the observation we are currently looking at. So this can only be +1 or -1. Yeah? So this will so this will just change the sign of that alpha I guy here. So the most important part is this thing here, and this is basically simply such a Gaussian bump, which is centered, as you can see, around the ith observation. Also, remember that only some of these guys here will be non-zero, so they will be active in the sum, because they will only be non-zero if they are support vectors. So this will not be visible in my upcoming visualization, because for this example here, everything will become a support vector. But in general, remember, some of this stuff, some of these bumps and associated observations will simply skip because they might become non-support vectors in the general case. So what I'm now doing is I'm going through this step by step. So I'm visualizing like partial sums where I'm adding in the first, the second, and the third component, and you can see how these bumps then mix together. So I'm starting down here. So that's our first Gaussian bump, which is centered around one of these 2 green guys here. I'm actually not exactly sure which of the 2, but it's just one. And now we add the second, and you can see how they kind of smear together in a certain sense, and they form a larger bump together, which is not unimodal, right? But it's just 2 bumps very close to each other mixed together. So in a certain sense, it's a Gaussian mixture model. Here's the third one from the negative class. You can see how it goes down because of the yi equals -1 label. Now we're adding a red guy in. A second one, again, you can see the smearing effect. And the third one. And what we now can do, and you can see how this creates this bumpy surface, where we have like positive mass, or positive decision mass in a certain sense, in the areas where red points are lying, negative downwards mass in areas where the green observations are lying. If we move away from all of the observations, we basically get this regression to the mean effect, where everything kind of becomes 0 or close to 0, and we therefore have a very low confidence what actually happens in these areas. And we can also now mark the level set of 0. So this is exactly where our decision boundary now lies. So all of the points here which have an associated height or an associated F score of exactly 0, and you can now see that we would classify everything down here as green, so as -1, and everything up here 2, and the remaining area would be classified as +1. And I hope this really helps you to understand that this is, it's obviously a very flexible local model. From this, you can basically learn arbitrary structures, if you have enough data available to you in all interesting areas, of course. Okay, further couple of comments on the kernel width, so we understand even better now with more points. I'm not going to say in more realistic data situations, this is still toy examples, but at least it's not only 6 points. So we can understand how the kernel parameters now affect the shape of the decision boundary. So if we use a very large gamma, if we use a very large sigma and very large sigma squared, so the width of the kernel becomes super large, that kind of smears out across everything, and then the resulting decision boundary will become super smooth. So in the limit, the decision boundary will become almost linear. That's actually provable. Down here I have used, as many times before, the libSVM software. So the libSVM software has the kernel, the RBF kernel here specified through this gamma parameter, so watch out for that. So that's the inverse kernel width. So if this guy is small, we have this very smooth decision boundary effect. And here you can see this is really an RBF kernel. It's not a linear SVM, but it nearly looks like this. And it's appropriate for this data set here, where kind of the Bayesian decision boundary, the base classifier would probably be a hyperplane classifier. And on the right hand side, again, you can see here our good old friend, the spiral data set. Again, I'm setting the gamma to a very low value or the sigma to a very high value. And you can see that because of this, my model now is not flexible enough. So I can actually introduce a very strong bias now for smooth decision functions, and in this case it's too strong. Okay, so I'm underfitting my data set here. On the right hand side, you can also see this from this very high training error, which is nearly 50%. And if we go to the opposite direction, so if we take very small sigma parameters and hence super large gamma parameters, we create very, very tight tight bumps of very small width around individual data points. In that case, usually every data point becomes a support vector, and our RBF SVM totally overfits the data by basically modeling each training point exactly on its spot where it's lying. And if we move away from this by just a couple of, millimeters, so to speak, we have no idea how to generalize to these other test points. We basically immediately go down to a decision score of nearly exactly 0, which would be, so basically we are inside of the margin and close to the decision boundary nearly everywhere. And this is, obviously totally overfitting. So we're basically learning the data by heart and we have no idea how to generalize beyond it. So I'm really overdoing it here on the left-hand side. For this situation, where this would probably be a good model, a good decision boundary. And here I'm slightly overdoing it on the right-hand side for the spiral data set. So here the fit is actually not that bad. But we can still see the overfitting effect a little bit because the training error is about half as large as the testing error. So probably still want to go for something that's a little bit smoother here.